Hello, everyone. Welcome to Telops webinar on additive manufacturing. We'll give a few seconds for the other people that are coming in to join us. Everything seems to be in order, so let's get started. So welcome. Today, we'll be discussing how to optimize your additive manufacturing process using high-speed infrared imaging. So my name is Antoine Dumont. I'm a field application engineer at Telops, and I'll be joined by Xiaohui Zhang, a PhD candidate from the University of Toronto. Sorry about the invite. In the invite, some of you might have seen that we mentioned it was a postdoc fellow. A simple misunderstanding, but it's only because of Xiaohui mature and long experience in the field. Now, before we fully get started, we always like to share a little poll with the attendees. And let me put that on your screen to understand a little bit more about the experience of our audience. So let's launch this. You should be able to see this on your screen now. So just want to know how you would rate your knowledge of infrared imaging. Let's take a look at our result. So that's really interesting. So no thermal imaging expert per se. So quite a few people that do not have direct experience at all with the technology. Quite a few that did consider it, and some of you that did have experience previously with infrared imaging, where it'd be Telops or another kind of camera. So that's great. Hopefully we get some very interesting questions at the end. Do not hesitate if you have any kind of question. We always love to get every kind of question during our webinars. So let me hide the poll. Here we go. So I'll start the webinar just by giving a little overview of Telops with her product line and just showing the kind of applications that the high-speed infrared cameras are used for. Afterwards, I'll transfer the presentation to Xiaohui and the recent advances in Professor Yu Zou's group. All of that, he'll be talking about this in more details. Of course, we'll conclude with more of a question and answer section at the end. So a quick note about Telops. Telops was started in 2000 in Quebec City. We're still there. This is where the headquarters are. We have over 90 employees, and those people come from a variety of backgrounds, quite a few people with advanced degrees. We have a very large section of R&D, and we're really proud that we've basically established ourselves as world leaders for thermal imaging solutions. Yes. Now, there's plenty of different products and solutions that I won't be talking about directly in this webinar. I just want to mention that we do have hyperspectral and broadband cameras or multispectral cameras. And one solution, one service that's recent is the aerial methane leak detection service. Telops also recently acquired LR Tech, a company near Quebec City that will really complement the technology that Telops has been developing over the years. Now we can see here our family of products. We have the hyperspectral cameras on the left. So we won't be talking about that technology exactly during this webinar. We have the multispectral cameras, which is a bit of an in-between type of system between hyperspectral and broadband cameras. We have 8 filter wheels that spin continuously to get an acquisition with multiple spectral windows. And then we have our broadband cameras. We have high dynamic range cameras, a recent addition to this line. The HDR M700 is really amazing, but not the point of the webinar today. The fast cameras, which is what the data we'll be discussing today, has been acquired with. And then the entry-level spark cameras or radio cameras, which are coming, did just come out this year. So a very quick glance at the kind of application that these cameras are used for. We have ballistic combustion experimental mechanics, which is growing quite a bit in recent years. There's gas detection and mineral identification. That's more in the realm of hyperspectral imaging. IR signature for typical defense and research, defense lab research applications. We have additive manufacturing, which is very much a very, I would say, a fascinating field and very much the fastest growing one in this family here. And we'll see plenty of very interesting data with Jiahui today. And finally, some non-destructive testing that we can see. That's an example of a chip with some defect or hotspots that we can detect. Now, for today's topic, the typical camera that we would want to use is a fast camera. For additive manufacturing, we need a very, very good radiometric accuracy, a good measurement of temperature in the hotspot of the melt pool. We typically also want to go relatively fast, depending on the kind of research, the kind of measurement we want to obtain, but it does require a certain amount of speed. So in the Telops line of the fast cameras, all of these cameras contain the permanent calibration that allows for an automatic exposure control, so the user doesn't have to play with the exposure time when there's a quite dynamic range in the scene. It can go up to 3,000 frames per second in the full frame mode, but if you do some windowing, reducing the amount of pixels in your window, you can go up to 100,000 frames per second. So all those cameras have a buffer for high-speed acquisition and have different filters that can be used depending on what you're looking at or the intensity of your scene. Weatherproof certified as well, and all of these are available in SWIR, so shortwave, midwave, and longwave categories. And another example here, so that's a split Hopkinson bar that was done at a very, very high speed, around 40,000 hertz, so a very slow playback speed that was available with the cameras. Now, I do want to mention, you might have noticed behind me, behind my in my webcam behind me, it's a bit of a peculiar wall for soundproofing. We are setting up a new studio, so we're very excited to share that with as many people as possible. The idea is to have a new setup, a new studio to make it more interactive. So we'll have very interesting IR Tech Talks with an increased interaction with the public, with the clients, with everyone that wants to be attending. Some more targeted product and software demos that we can do in here. And we'll even be offering some live testing measurements with the relevant tools and instruments. Obviously, at headquarters, it's much more convenient, or it's much more easy to have multiple cameras, different lenses that are available. We have black bodies, we have different equipments that can be used that we're not necessarily able to bring with us to customers, to different clients that are asking for demos. So we'll be encouraging people to contact us about any kind of ideas that you might have for testing and demos. And that can be done for broadband cameras, multispectral, and multispectral cameras like we have on the right here. So keep an eye on that for 2025. Now, to talk about today's topic a bit more, additive manufacturing is a really interesting and a really critical field of research nowadays. It's a very fast process with quite high temperatures, especially in that melt pool region that we have here. There are different families of additive manufacturing, of course, and Professor Yu Zou's group are focusing on a specific one. But typically, we're talking about high temperatures for most of those families. This is a great example of a video that was taken at the very beginning of when Professor Zou's group acquired the cameras from Telops, doing some testing. Sorry. And this video in particular was processed using EHRI. So the camera is basically taking a a recording at different exposure time, one frame after the other. So we have a very low exposure time here and quite a high exposure time. And the software is able to recombine those together to have a good signal to noise ratio. So we have a clear background and we have a clear view of the melt pool at high temperature, combining those images. Now, additive manufacturing has been growing and has been part of a more common area of research in the last 2 decades, probably. But I would say it's not necessarily a new technology. We can see here a printed house wall that was done in the 1930s. Technically could be considered additive manufacturing. It's just a very fascinating little bit of history. People have been thinking about ways to process, to print and do some manufacturing that way for quite a long time, almost 100 years now. But with this neat little video, I'm gonna transfer the presentation to Xiaohui, and let me just transfer that to you. I know he is with us, so here you go. It's all yours now.
Okay. Thank you for the invitation. Thank you for the introduction. So I guess everybody here can hear me. Is that okay?
Yes, we can hear you just fine.
Okay, so yeah, I'm going to share my screen. So yeah, let me know whether I share the correct screen or not. So is that presenter mode?
You are. We don't have the full screen. We have the
presenter mode.
Your presenter view right now.
Okay, so can you see my full screen? Okay.
Right now it's perfect. Yeah.
Okay, perfect. Okay. Hello everyone. So yeah, welcome to the webinar. So it's our great honor to just have this opportunity to talk about our recent research about optimization of additive manufacturing process with high-speed air camera. So before talking about the real contents, I will give a brief introduction about our lab. So the laboratory for extreme mechanics and additive manufacturing. So our PI, the principal investigator in our group, is Professor Yu Zou, who is an associate professor and a Dean Sparks professor from Department of Materials Science and Engineering at University of Toronto. So in our group, we have 4 different research fields. The first one is metals. So we care about high entropy alloy, nanocrystalline alloys, quasi-crystal, titanium, and different kind of metal alloys. So for mechanics, we are focusing on multi-scale mechanics, and we are carrying out experiments for high strain rate or high temperature deformation, especially under the extreme environments. And for manufacturing process, we are not only working on additive manufacturing, for example, laser powder bed fusion and laser direct energy deposition. We also care about cold spray, powder metallurgy, all other fields. And for machine learning, we are trying to use machine learning to accelerate the material discovery and trying to use computer vision approach to fulfill some specific tasks. So after talking about our lab, I will give a brief self-introduction. So my name is Jiahui Zhang, and I'm a PhD candidate also from the Department of MSE at the University of Toronto. So my thesis topic is about machine learning aided optimization of metal additive manufacturing process, and my research fields contain additive manufacturing, machine learning, numerical simulation, computer vision, and obviously process monitoring. So let's talk about this project. So first of all, I will give a brief introduction about laser direct energy deposition, in short LDED. So first of all, I will talk about the mechanism of this technology. So LDED uses a laser source that is focused on the substrate, forming a small area we call melting pool, and simultaneously melting the feedstock material delivered into the melting pool in the form of the metal powder or the wires. So this technology has been widely used in a lot of advanced fields. For example, the aircraft engines or some biomedical implants. So the recent study point out the market size for LDD has been growing rapidly within recent years. So one of the main advantages of LDD technology is to fabricate complex geometry with a higher accuracy. So among all the different geometries, thin wall structure is very critical for the LDED process due to its widespread adoption and the challenges present during the fabrication of thin walls. So in short, if we can fabricate high quality thin wall structure, we can use LDD process to fabricate more complicated geometries. So currently, the challenge facing when we fabricate the thin wall structure is the dimensional inaccuracy. So this figure demonstrates like two main common situation we will face during the fabrication of the thin wall. So the top part demonstrates the layer surface unevenness, and the bottom part demonstrates the excessive buildups. So the reason to cause this situation is the selection of inappropriate processing parameters. So during the printing process of LDD process, there exist dozens of the printing parameters. So the laser power, scan speed, and feeding rate are recognized as the three main factors that has a dominant impact on the final quality of the fabricated components. So the LDD process always fabricates components through layer by layer mechanism, which means like if we can find the optimal processing parameter for fabricating single layer melting tracks, that means like we can guarantee the quality of the fabricated thin walls. So to achieve that goal, we carry out high-speed experiments to try to investigate the influence of different processing parameter in the quality of the fabricated thin walls. So here is the selected region. So here is the processing, designated design space we have selected for this experiment. So for the laser power, we select the laser power from 310 watts to 600 watts with an interval of 10 watts. And we have three different scan speeds changing from 4 millimeter per second to 12 millimeter per second. And for the feeding rate, we have 4 different options changing from 0.2 RPM to 0.8 RPM. So in total, we can generate a design space which contains 360 different processing parameters. So here the image demonstrates how we fabricate different melting tracks. So here's the one plate with a fixed feeding rate, and the length of the melting track is set to 10 millimeter, and the distance, the gap between each of the melting track is set to 4 millimeter. And for each column, we will fabricate 15 different melting tracks under different laser powers. And in total, for each of the plate, we will generate a plate with 90 different melting tracks under the same feeding rate. And for traditional method, to evaluate the printing quality, they typically use a 3D microscope to scan the melting track fabricated during the printing process. For example, here we demonstrate the melting track fabricated under the lowest energy density, which means like when we have lowest laser power and highest scan speed with the lowest material feedstock. We use the lowest feeding rate to fabricate this melting track, and we use the 3D scanning technology, we can get a 3D geometry for this melting track. And in contrast, we compare that result with the melting track fabricated with the highest input energy density, which means like we use the highest laser power, lowest scan speed with the highest material feedstock, which means like we use the highest feeding rate when we fabricate this melting track. So as we can see, like when we change the processing parameter, the 3D geometry of the melting track show a huge difference. So we can also summarize these results for this melting tracks. So from this 3D scanning results, we can get the building volume, surface roughness, the width of the melting track, and the building height of the melting track. We can get a lot of different information for this melting track. So here we demonstrate the melting track information, especially the melting track volume across various processing parameters. So here we can see, like by increasing the laser power, I need to use the laser pen. So by increasing the laser power, we can see like the melting track volume slightly increase. But when we decrease the scan speed or increase the feeding rate, which means like at the unit time, you will have more material feeding into the melting process, or more material has been melted. So we can see the melting track volume increase dramatically. So since the feeding rate increased exponentially, so when we make this plot, so the y-axis of this plot increase exponentially. So after talking about the melting track volume, so the next thing is like, since like all those kind of melting tracks, they are printed during the different scan speed. So we also calculate the different building rate under different processing parameter. So the building rate is calculated by the melting track volume divided by the printing time. So as we can see, everything has changed. So which means like when we have the lower scanning speed, we will have higher building rate. and the influence of the laser power in the building rate became significantly. So for those kind of information, we can make some conclusions. First, increasing the laser power slightly increase the melting track volume, but significantly boost the building rate. The second thing is reducing scan speed enlarge the melting track volume, but lowers the building rate. The third thing is increase the filling rate enhance both the melting track volume and the building rate. The first one is as the filling rate grows exponentially, the melting track volume and the building rate increase more granularly, suggesting a saturation effect. That's how the previous work typically do when they are trying to evaluate the printing quality. However, those information or those features, melting track features, only can be extracted after the printing. To really understand the printing process, we should extract some information or extract some features during the printing, something we call in situ features. So to achieve that goal, we need to understand the formation of the melting track. So during the formation of the melting tracks, the melting pool always plays a very critical role. So the melting pool, the instability of the melting pool can induce a lot of different defects. For example, the surface roughness, the porosity, and the cracks. So previous study used some other technologies, advanced technology, for example, the synchrotron X-ray, to try to get information of the melting pools. So here is the video to demonstrate like how the melting pool can form the melting tracks. So let me find play the okay. So let me play the video. So from the video, we can see like the melting track is formed based on the melting pool, based on the form of the melting pool. However, we can also see like the existence of the metal powders block the view of the melting pool, which means like from this kind of technology, we cannot get the accurate information for the melting pool. So to make the conclusion, the first thing is the evolution of the melting pool during the printing process is critical for determining the melting track quality. The second thing is advanced tools such as synchrotron X-ray imaging system can provide insights into the melting pool dynamics. However, these instruments are restricted to synchrotron facilities, and which means like for the normal lab, you have no access to use those kind of similar facilities. And the imaging process is often hindered by unmelted metal powders. So to solve this problem, we are trying to use some other technologies, for example, the air monitoring sensors to try to get more accurate information for the melting pool. So here is the hardware setup in our lab. So we are trying to integrate the high-speed air camera with our customized DED machine. So you can see there we use a fixture to try to combine the high-speed air camera with the laser printing head. And this fixture can adjust the angle of the high-speed air camera and the height of the air camera, facilitating the focusing process. And we also shown the building substrate, same as the printing process. So here is a picture to demonstrate how we set up the whole camera. So you can see here is the fixture which can change the angle and the Z position of the air camera. So the hardware setup for this system is, so the camera we have used for this monitoring system is first M1K, as the host mentioned before, and the temperature range we have used is changing from 248 Celsius degree to almost 2000 Celsius degree. So the material we have used for this printing is the stainless steel, which means the melting temperature of this material is around 1400 Celsius degree. And the frame rate for the experiments we have used is 2000 Hertz, which means within 1 second we can capture at least 2000 images. And the resolution size we have used is 320 multiplied by 160 pixels. So here is the printing process, and this is the video we have captured by our phone during the printing process when we're fabricating the 10mm lens melting track. And here is the melting pool videos we captured from Telops M1K camera. So you can see like we can capture the different information of the melting pools, and the most important feature we care about is the melting pool area. So based on the air camera, we know every dimensions in pixel. So to transfer from the pixel to the real dimension, we need to know the scales. So in this study, we are trying to use a we are trying to use a stop sign with a fixed dimensions with a diameter of 7.85 millimeter to check to validate the skew and the distortion during the monitoring process. So here are the steps we are trying. Here are the steps to get to capture the images or get the information of the melting pool area. So we apply the AR camera to monitor the printing process, and we measure the distortion and set up a skew bar. And finally, we analyze the melting pool features, especially the melting pool area as a set interface. So by this AR camera, we can know a lot of information about the melting pool area. So we also analyze the melting pool area change across various processing parameters. So as we can see, like from the figure, we can see like as the laser power increase or the scan speed decrease, the melting pool area expands due to the higher input energy density. And the melting pool area grows with an increased feeding rate since more material deposits during the printing process. And the same saturation effect has been observed based on the AR camera, which means like even we increase the feeding rate exponentially, the melting pool area cannot grows at the same rate. It always grows at a slower rate, indicating the saturation effect. So those information is only the mean area of the melting pool. So with the assistance of the high-speed AR camera, we can not only get those information, since those information can be easily captured by a normal AR camera. So with the assistance of a high-speed AR camera, we can get more. So here is the printing stability we analyzed from the AR camera. Since this is an unpublished work, so I don't recommend you guys to just capture these images. So we demonstrated the images. We demonstrated the melting point area evolution under a specific processing parameter when the power equal to 310 watts, the scan speed equal to 12 meters per second, and the feeding rate equal to 0. RPM. So under this processing parameter, the printing time for the melting track will be less than 1 second. So without the high-speed feature of the AR camera, we cannot capture so many melting pool images, which can be used to analyze the melting pool area fluctuation during the printing process. So we also compare these images. With the 3D scanning geometry of the melting tracks. As we can see, there exists the correlation between the melting pool fluctuation and the melting track and the melting track 3D geometry. And we also compare this case to another case with a more stable printing. So we change the processing parameter to the power equal to 390 watts, the scan speed equal to 8 meters per second, and the feeding rate equal to 0. RPM. Under this kind of conditions, we can capture around like 2,500 images of the melting pool during like I think 1.25 seconds printing. And you can see under this kind of processing parameter, the printing stability increases a lot, which means like we have a longer stable printing region with a minimum fluctuation or coefficient variation of the printing. And we also compare this melting pool fluctuation with the melting track 3D geometry, and we can also observe there is also a correlation between the melting track fluctuation with the melting track scanning geometry. So those observations tell us that we can easily use the melting pool, the in-situ melting pool feature we extract from the high-speed AR camera as an indicator for the final features we can extract from the melting track. So we can also use those features to do some closed-loop control to try to increase the printing stability. So in this slide, I'm trying to talk about the printing stability under different processing parameters. To make all those plots, we increase the feeding rate from the bottom to the top. So this one is under this PV combination, but at 0.2 feeding rate. And we increase the feeding rate from 0.2, 0.4, 0.6, and 0.8. And we also change the processing parameter under different PV combination. And in that one, we select the different P and V. And we also keep the same input energy density, but we change the PV combination. And from those kind of figure, we can draw some conclusions. So first, the processing parameter not only affects the building rate, but also it will affect the printing stability. And the second thing is the effect of a processing parameter in the printing stability doesn't follow a consistent trend. So we need to analyze the case. We need to analyze those cases one by one. But the only thing we know is ideally achieving the longest stable printing region with minimum fluctuation leads to highest printing quality. So however, those printing stability is only for one single layer melting track. As I mentioned before, that printing stability will influence the fabrication of the thin wall structure. We did a case study based on this hypothesis. So we select 4 different processing parameters which has different printing stability. So which I shown here, 1, 2, 3, 4. So the case 1 and case 3 I have shown before, like I shown before is because like the case 1 has the lowest printing stability, while the case 3 has the highest printing stability. And I think the case 2 and case 4, their printing stability among the case 1 and case 3. So in this case study, we are trying to use the same processing parameter to print a thin wall structure with a designated height of 5 millimeters. And the layer thickness is set to a scale multiplied the melting pool height, which the information we extracted from the polished melting pool area. So here is the results for the case study. So as we can see, the processing parameter under the case 3 had generated the thin wall with the highest printing quality, while the thin wall structure and the processing parameter of the case 1 has the worst. And even compare the height of the thin wall, we can see like the case study 3 has the highest accuracy, which means like we should not only use the building rate as the indicator for the printing quality, we also need to care about the printing stability. So one thing I want to mention here is the printing stability can be only analyzed from a high-speed AR camera. The reason why is like high-speed AR camera, they have two advantages. The first one is high speed. As I mentioned before, if you didn't have high speed, you can only capture like 10 images under a certain processing parameter. You cannot see the fluctuation of the melting area. And the second thing is AR camera can help us accurately recognize the melting pool boundaries, since you will easily know the temperature of the melting pool boundary based on the AR camera, and you can use that number to recognize the melting boundary. With a normal like high-speed camera, you will never get the accurate information for the melting pool boundaries. So to make a summarization of this work, first, the processing parameters in the LDED process are critical for determining the final quality of fabricated thin wall structures. And the second thing, as I mentioned before, beyond the melting track features, analyze the post-processing. Fluctuation in the melting pool area during the process are also critical for quality assessment. Using a high-speed AR camera, melting pool characteristics can be captured with higher spatial and temporal resolution. A correlation exists between the melting pool area fluctuation and the change in melting track height, emphasizing the printing stability significantly influence the quality of the printed thin walls. So that's all for this work. If you have any question, we are welcome. And I also shown the QR code for our website and the PI email and the presenter email. If you have any question, you can send us the email. I think that's all.
Thank you very much, Zhuahui. This was really, really interesting. So I'll invite anyone that has a question to go into the GoToWebinar tab, the questions tab. You can write your questions down here, and we'll happily answer any of your questions. So while we're waiting for some questions, I might have a few questions myself.
Mm-hmm.
Since we're talking about IR imaging,
Mm-hmm.
the emissivity is always an important factor to consider when you look at different temperatures. In your work, do you have any issues with, we're talking about metal alloys, so typically a low emissivity.
Yes.
Do you have any issues with that kind of measurement or emissivity change? Since we're talking, there's a melting happening as well. Do you notice any issues or something that has to be considered?
Yes. So let me go back to my slides. I think it's slides. Yeah. So when we characterize the temperature during the printing process, I think we did face the problem of checking the emissivity. So there are several ways to check the emissivity, the first thing is you can read some literatures since we are not the first group in this field. So I thought like a lot of groups they mentioned like for emissivity for stainless steel is 0.3. So the thing is like we use that number since based on the Telops software, you can easily change the emissivity and you can get the temperature calibration after the emissivity, after you inputting the emissivity. And we get the information for our melting pool area, as I mentioned before, and also the melting pool, the height. So we compare this information with the melting pool head we can extract after the sample polishing. And we realize like the melting pool head we extract from the air camera is almost similar as the the information we extract after the post-processing. So at that time, we can guarantee we use the correct the emissivity for the whole process.
All right, very interesting. Thank you. If I don't see, let's see. Well, wait a little bit more. I have another question for you.
Mm-hmm.
This is a kind of manufacturing process that is used for a multitude of different things.
Mm-hmm.
So in the goal of applying this in a more industrial context,
Mm-hmm.
is there a possible like feedback loop for IR imaging that would improve the process almost in a live way, like a very direct feedback? Like how quickly could that feedback be done for like doing that in the industry?
I think that's a good question. Like, I mean, like the final goal for using the air camera is trying to build the closed loop control system to try to change I would say, to adjust the printing instability issue. Like I already show one picture about like I call it unstable printing, like the figure shown left. So we did try some method or algorithm to try to analyze those information. So I feel like for the air camera we have in our lab, so the capturing image is not an issue. Like it can easily capture a lot of images. So the only challenge is how you analyze those data. Since like we are trying to use some machine learning technology to try to analyze those data and trying to provide the feedback at the same time and put the feedback into our machine to change the processing parameter. So that's what we are trying to do in the next step.
Okay, great. Well, good luck with that. All right. Well, for those of you that are still here, please, if you have any questions, let us know. Maybe last chance. I have maybe a little question left. If you can go back to that setup that you had in your lab,
Okay.
with what you had with the camera hanging at a certain angle.
Yeah. Okay. That's I think that's 11. Oh, sorry. That's 9. Okay.
This one, yes. So we can see that the camera and the lens they're fairly close to the process that's happening at quite a high temperature.
Yes.
Do you is there a danger zone, you would say, for this kind of printing process? Is there any kind of splatter, any kind of danger for equipment?
Yes. I should say yes. Like so during the printing process, there are a lot of sputter generating the printing process. So it probably have some damage to the lens. But I mean, we already used that one for the whole year, but we never seen any damages for the air camera. So we do try to build some protective window to try to protect the lens, since we know like a lens is super important for capturing the images. So we are trying to build, and I think we already bought the material, like the window, but we are trying to think about how can we assemble this window to our air camera, and we still need to keep the distance between the printing head and the protective window. So yeah, I would suggest you just prepare a window to try to protect the lens.
All right. Yeah. Okay. Well, thank you very much, everyone, for attending. I'll just switch it back to my presentation. So if you have any questions, feel free to contact us. Nope, it's not showing. Sorry about that. So if you have any questions, feel free to contact Telops on our website, transitioning to the Exosens website, which is now the family of different companies that Telops is part of. You can contact us either sales@telops.com or FAE@telops.com, which would contact the field application engineers such as myself. And otherwise, we have a multitude of social media channels, that you can where you can see a lot of interesting information and videos for different applications, in particular for additive manufacturing for today. So you can write to us in any way, and I want to say a big thank you to Xiaohui for today's webinar. It was very interesting. So thank you very much, and have a great day.